Hello and good afternoon, everyone. First, I want to thank the conference organizers for having me back, as well as allowing all of us to share our work on extractables and leachables. Today, I am presenting on sort of a sequel to what was presented in the 2019 ENL USA RAPRA conference by Dr. Xiaoshen Yu, in which we are looking at migration kinetics from container closure components. Our research on building kinetic models was performed as a collaboration between our USA site in Middleton, Wisconsin, and our PPD Athlone location in Ireland. Let me start with some background information. Extractable and leachable studies typically consist of three types of studies. One of them being a controlled extraction study, where you are exposing the container closure components to multiple solvents at harsh conditions to generate an extractables profile. There is a simulation study in which you are using accelerated conditions in a solvent simulating that of the drug product matrix and its extraction power and exposing the container closure components to that. Finally, there is a leachable study, which you are actually testing the actual drug product stored at its intended storage and accelerated conditions. There are many reasons to do kinetic migration studies. A couple of them I have listed here. One of them being that you could use migration kinetic information to predict long-term leachable amounts from data off earlier time points. You could use migration kinetic studies to predict leachable amounts at different temperatures, like versus 25C versus 5C at the same time point. Finally, you could use migration kinetic studies to help to choose the appropriate temperature and duration for a simulation study. Unfortunately, the migration process is quite complicated. There are a lot of factors that go into compounds migrating from polymer materials. Some of those factors are things like you have the migration of compounds from bulk material to the surface through pores in the material, the migration of compounds from the surface of polymer material to the interface or the diffusion layer and vice versa, the diffusion of compounds from the diffusion layer into the bulk solution, and leaching really isn't completed until an equilibrium is established between the solid phase and the solution phase. A lot of different factors go into the migration process, and I will touch on this again later in the presentation. And that makes modeling this mathematically quite challenging. There is a mathematical model in using Fick's law of diffusion. However, its practical use is limited, and it's actually a very complicated model and has a lot of different parameters. And so determining those parameters to make the model useful is quite challenging. So developing empirical models based on data generated is a more practical approach. One of these studies uses models focusing on API aging, which is the ASTM, or the American Society for Testing and Material F198016 model. So I'll start by explaining this model in a little more detail. So the ASTM model was developed as a guide for accelerated aging of sterile barrel systems for medical device testing. It had previously been proposed as a way to calculate and justify accelerated migration testing for extractables and leachable studies. The technique is based on an accelerated aging factor, or an AAF, and equated that to the accelerated temperature minus the reference temperature, or the normal use temperature, and the Q10 aging factor. That Q10 aging factor we will explore more with some of our empirical data. And then you can relate this to study duration, as shown at the bottom of the slide there, where the aging time at the accelerated temperature is equal to the aging time at the reference temperature divided by that accelerated aging factor. So this then allows us to correlate time and temperature together. The goal of the original study was to develop kinetic models for the three different projection models of concentration versus time, concentration versus temperature, and temperature versus time. And we wanted to take these empirical models and compare them against the previously established empirical ASTM model that I just went through. So the initial study, the container closure component we investigated was bromobutyl rubber stoppers. We looked specifically at BHT from the rubber stoppers sitting still in incubation and allowing only time or duration and temperature as factors for extraction. The solvent chosen was 50/50 IPA water, a solvent that is commonly used in extraction studies. The temperatures chosen were 5, 25, 40, 50, and 60 Celsius. The duration and time points chosen are listed out on the slide, but range from 4 hours to 180 days. Lastly, we used 20 mils of IPA water solvent as an exposure with 3 stoppers for each sample. For the analysis, we used an HPLC UV with a wavelength of 220 nanometers, and the column and mobile phase information are provided here as well as the gradient. So I don't need to talk about this too much since it's all here on the slide, but I have BHT shown at the bottom. This is a common antioxidant in polymer materials and a well-characterized extractable from container closure components, which is why we used BHT as the model analyte throughout this study. So I will get into some of the results. I'll start with concentration versus time, where we are looking at projecting future time point extractables and leachables at the same temperature. Having this model would allow us to project the leachable amount at the end of a shelf life based on data from earlier time points. In this first plot shown here, we have the extracted BHT amount on the y-axis versus the duration of the study on the x-axis, and each curve corresponds to a different extraction temperature. As expected, the extracted amount of BHT increased with time as well as increased with extraction temperature. So the higher the temperature, the more BHT that was generally extracted. I will point out that in this plot, most of the data goes out to 180 days, while the higher temperatures of 50 and 60 degrees C, you will only see it out to 90 days. And that is because we observe significant degradation of BHT at those higher temperatures out at 180 days. And we are still working on characterizing some of those degradants to fully plot out the total amount of BHT in the degradants. And that is why you don't see that data plotted here. So from the curves, we were able to develop a general equation shown in bold there, where C is equal to a constant A times the natural log of time plus a constant B. So here is a summary of those general equations we gathered from each of those plots to make a general equation, where C equals the extractables or leachables concentration or amounts. A and B are constants that can be derived from the existing time points data, and T equals time. So for this, theoretically, with two or more extractable and leachable time point amounts, you could project the leachable amount for future time points. Now I will move on to the concentration projection versus temperature at a given time point. This model is used for projecting the concentration of an extractable leachable for different storage temperatures at the same time point. For example, if we know the leachable amount at 25C at the 24-month time point, can we project the 5 degrees C leachable amount at that same time point? From the data, we were able to develop a concentration projection model related to temperature. In this plot, we have BHT concentration plotted against extraction temperature as shown here, for a given time interval. Each set of data plotted, each curve, represents a given time interval in days. As the figure shows, the extracted BHD amount increased exponentially with extraction temperature. We were then able to use the equations generated by each curve, just as we did for the last graph, to figure out an average concentration equation shown on the top, where a projected concentration, or C2, divided by a known concentration, or C1, equals a constant 1.045 raised to the difference in temperature. So we took that constant of 1.045 that we generated based on the average of curve equations generated on the last graph and calculated a Q10 value of 1.55. And this allows us to say that we could use the ASTM model with a Q10 value of 1.55 for a concentration projection of BHD extracted in the same material with the same solvent. This suggests that the ASTM model is appropriate for calculating and predicting extractable and leachable amounts at one temperature from amounts at another temperature when a suitable Q10 value is used. Lastly, we will look at duration projection, looking at different temperatures across a constant concentration. So if we wanted to know for a 5 degrees product with a 24-month shelf life, how long would it take to achieve that same leachable amount at 40 degrees C? Using the previous graph of concentration versus time that I just went through, we were able to develop a model for predicting the extraction temperature and duration of a study at a constant extractable amount of BHT. The extraction temperature data was generated by drawing a constant BHT line amount, such as 20 micrograms per stopper, across each time interval curve. So plotted here, we have the extracted time of the study to the extraction temperature for a given amount of extracted BHT. As expected, the amount of time required to achieve a specific extracted BHT concentration decreases with increasing extraction temperature. So to break that down a little further, we can see that for a given amount, for example, the 90 micrograms per stopper, the yellow curve in the middle there, it takes less time to reach that amount at higher temperatures. So as the temperature increases, you can extract that amount faster. Using the equations generated from each of the curves plotted, a generic third model was developed that could be used to predict the duration of the study required to achieve a certain amount of extractables at a given temperature, where you have T2, or the predicted duration, over T1, the reference time interval, is equal to the constant 1.110 raised to the power of T1 minus T2, or the reference temperature minus the accelerated temperature. We then put this into the ASTM model to back calculate the Q10 value. For stopper extracted BHT, this was 2.85. This suggests again that the ASTM model is an appropriate model for calculating the accelerated aging time when a suitable Q10 value is used. So to just kind of summarize what I've gone through so far, we developed three equations for BHT kinetics as shown here in equations 1, 2, and 3. For equation 1 being a concentration projection at different time points, equation 2 is a concentration projection for different temperatures, and equation 3 is a duration projection for different temperatures. And we were then able to equate equations 2 and 3 into the ASTM model and calculate an experimental model Q10 value as shown at the bottom of the slide. And for the concentration projection, we had an experimental Q10 of 1.55. And for the duration projection, we had experimental Q10 of 2.85. which is fairly comparable to the conventional Q10 value of about 2 for first order kinetics, which is a more conservative number. Which brings me into the current study. We wanted to see the effect that shaking would have on the empirical mathematical equations and if it would speed up the migration. The previous study had the rubber stoppers sitting stationary for a given time and temperature. We added the element of shaking with temperature and time. The same models were investigated: concentration versus time, concentration versus temperature, and temperature versus time. The overall goal was to determine the limiting step. We used the same overall study design where we used the same rubber stoppers with the solvent medium of 50/50 IPA water. We used the extraction temperatures of 25, 40, and 50 C, so we removed the 5 C and 60 C. We abbreviated the study and added some additional early time points ranging from 2 hours to 30 days. We used the same 3 stoppers in 20 mils of solvent for extraction. The major difference was the use of incubated shakers, where we shook the samples at 100 RPM for the duration of the study. We chose 100 RPM as it is a commonly chosen speed for extractable and leachable studies. The same instrument method was used throughout the study as well. As you can see on the slide, we tried to keep everything as similar as we could to best be able to compare the two data sets to see the effect that shaking would have on BHT extraction. So we will be going through the 3 mathematical models, starting with concentration versus time to compare the two sets. In the plot shown here, we have the extracted BHT amount on the y-axis and the duration of the study on the x-axis, and each curve corresponds to a different extraction temperature for the shaking samples. As expected, the extracted amount of BHT increased with time as well as increased with extraction temperature. So the higher the temperature, the more BHT that was generally extracted, which matches the trend from the previous results. And from this data, we were able to use the same general equation shown above the plot in bold there, where we have concentration is equal to a constant A times the natural log of time plus the constant B. What is new is that the shaking did not affect the amount of BHT extracted. This graph here has BHT amount plotted against the time points for both the shaken and non-shaken samples. You can see they all followed the same trend and had about the same amount of BHT extracted within experimental variation. And you can see the same general equation for both experiments. Shaking did not have an effect on the amount of BHT extracted. Shaking will not accelerate the migration of BHT from the stoppers. The rate controlling step for the butyl rubber stoppers is the polymer surface and the rate at which it allows leachables to migrate into solution. When you agitate the solution, it will accelerate, but it doesn't appear to do that for this material. Next, we will look to see how much shaking would affect the projection model for concentration versus temperature using the same time point. From the data, we were also able to develop a concentration projection model related to temperature for both shaking and stationary results. In this plot, we have a summary of the shaking results, where we have the BHT concentration plotted against the extraction temperature for a given time interval. We were then able to use the equations generated by each curve to generate a concentration equation shown at the top, where a projected concentration, or C2, over a known concentration, or C1, equals to a constant raised to the difference in temperature. For the stationary results, our constant was calculated to 1.045, and for shaking, we got 1.035. We then back calculated to get the Q10 factor of 1.55 for shaking and 1.41 for shaking and 1.55 for stationary. The difference between the two data sets are within experimental variation and aids in supporting that shaking does not impact the extraction of BHT. And finally, we will look at temperature versus time using the same amount to see what effect shaking had on this calculation. So here we again equated the time of the study in hours to the extraction temperature for a given amount of extracted BHT. And using the equation for each of the curves plotted, we were able to develop a model for duration projection where you could predict time given different temperatures at a given amount of extracted BHT, and that is shown in the equations above. We have both the stationary and shaking extraction equations, where you have T2 or the predicted duration over T1, the reference time interval, is equal to the constant 1.11 for stationary and 1.094 for shaken, raised to the power of T1 minus T2, or the reference temperature minus the accelerated temperature. Then we back calculated to have a Q10 value of 2.85 for stationary and 2.82 for shaken. So again, there really was no effect seen here either by shaking. The two data sets are well within the experimental variation and aids in supporting that shaking does not impact the extraction of BHT. So to summarize, the migration process is very complicated. There are a lot of factors that go into compounds migrating from polymer materials. From the data shown today, migration is controlled from within the stopper's polymer material. This is the limiting step. Shaking or no shaking will not affect leachables significantly. In general, there are three steps that can be used to describe the leaching process. One, migrating from the polymer material to the surface. Two, from the surface to the interface layer. And three, from the interface layer into the bulk solution. Generally, shaking can affect the interface layer thickness and the diffusion speed for the interface and the bulk solution, so steps 2 and 3. Therefore, it may affect the leaching speed of leachables. But the data shows that shaking did not affect the leachable speed. So this allows us to conclude that step 1 is the limiting factor for the speed of leachable migration. This explains why we are getting the same values with and without shaking. So in conclusion, we extracted BHT amounts, extraction time, and extraction temperature were evaluated and compared against each other. 3 empirical kinetic models were developed to predict the concentration of an extractable and leachable at a given temperature or time, as well as to predict the duration and temperature of a study given a target concentration. The only thing that can accelerate extractable and leachables from our data is temperature and time. Shaking or agitation has no effect. We are still trying to build a better model. I would especially like to thank my colleagues at the PPD Middleton site, especially Dr. Xiaoshan Yu and Dr. Benton Cartledge, and then also Dr. Rupinder Kaur, Nathan Hagg, Eric Hansen, Travis Lato, and Kevin Wu. Please let me know if anyone has any questions and I can answer them in the chat, or you can reach out to me by email at ashleyhellenbrand@ppd.com. Thank you very much for your time.